All right, so where we left off was that we were writing the algorithm for a system of equations and what it would look like. And so we had a system of equations that is y prime is equal to a function of t, y, and u, and then u prime is equal to another function g of t, y, and u. And so then I gave an example of what might it look like. And then for the algorithm, but for the algorithm, we need the endpoints A and B, we need the integer n, and we need the initial conditions alpha 1 and alpha 2. And then we find out h is n, and then we have t is equal to a, we have alpha 1 and alpha 2, and you can print t, y, and u, and then you must compute a slope for y and a slope for u. And so we do this step. And then the next step is to find the next slope for y. So the next slope, and it has to be done in this order. Okay, so that's the important thing about this is the order. So then, okay, why? Okay, stop. Thank you. All right. Okay. So now we have yk2, and that's going to be f. And now we have t plus h over 2. We're going to have y plus h over 2 times yk1. And then this is going to be u plus h over 2 okay, and then this is UK, UK1. Okay, and then we have UK2 is G of T plus H over 2, again, Y plus H over 2, YK1, and then U plus H over 2, UK1. Okay, so now we have those slopes, and then now we will do YK3, and that's going to be F of T plus H over 2. And now we're going to have Y plus H over 2. And then that's going to be multiplied by YK2. And then U plus H over 2 multiplied by UK2. And then UK3 is going to be G of T plus H over 2. And then Y plus H over 2 times YK2. And then U plus H over 2 times UK2. Okay, and then our last slope will be YK4. And that's going to be F, and this one is T plus H. And then we're going to have Y plus H times YK3. And then we're going to have U plus H times UK3. Okay, and then we're going to have UK4, and that's going to be G of T plus H, and then Y plus H times YK3, and then U plus H times UK3. And then we can update our solution, that is Y is going to equal y plus h over 6. And now I'm going to have yk1 plus 2 times yk2 plus 2 times yk3 plus yk4. And then I'm going to have u is equal to u plus h over 6 uk1 plus 2 times uk2 plus 2 times uk3 plus uk4. And then your t is going to be t plus I times h, and then you can print t, y, and u. And if you make a vector that saves your data, then you can make a plot of each of your solutions. Okay, so that's how we handle that. Now, why does this say systems of ordinary? Oh, because it does. It should be a D here. That's what looks weird. Okay. I want to say a little bit about multi-step methods, and then we are going to move on to the linear algebra portion, okay? Okay, so multi-step methods. So Euler and Runge-Kutta are single-step methods. That means we go from level T to level T plus H. Okay, so Euler and Runge-Kutta. These are single-step methods. Okay, and they use information from one level or one previous point to compute the next point. Okay, so multi-step methods use several points, okay, or use several prior points. To compute the next point. Okay, so they look something like this. So here's the problem. So the problem is y prime is f of t and y. And we know that a is less than or equal to t. We're going up to some value of b. Okay, we let h, we get y of a is equal to alpha, and our h is b minus a. And that's how we compute it. Okay, why are you giving me grief? All right, let's see. I'm going to try to close out. It always seems to want to get mad that I have stuff open. And then still tell me, I have everything closed. I don't know what else to do. Only have two things open. Okay. All right. So this method, y at I plus 1, okay, so is equal to a m minus 1 y at I plus a m minus 2 y at I minus 1 plus dot, 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 all the way down to a naught y at I minus m minus 1. Okay, plus some h, and then we're going to have b sub m times f of y I plus 1, I'm sorry, ti plus 1, ti plus 1, yi plus 1, plus bm minus 1 times f of ti yi all the way down to b naught times f of t I minus m minus 1, comma, yi minus m minus 1. Okay. Now, if bm is equal to 0, then the method is explicit. And if bm is not equal to 0, then the method is implicit. And by rule of thumb, for many numerical methods, implicit schemes always are more stable, but they are definitely more difficult to solve. Okay, so let's first talk about the two-step Adams-Bashforth method. Okay, so I'm going to just show you a couple of methods. So the Adams-Bashforth. So let's do Roman numeral 1. Okay, so for this method, we need to know y naught is alpha and y1 is alpha 1. And then y at I plus 1 is equal to y at I plus h over 2, 3 times f at ti yi minus f at ti minus 1 yi minus 1. Okay, where I goes from 2 all the way up to n minus 1. And this has with local error that is 5 over 12 y triple prime at ci times h cubed for ci for ti minus 1 less than or equal to CI less than or equal to TI plus 1. Okay. So that's the two-step Adams-Bashforth method. There is a three-step Adams-Bashforth method. Oh, and this method is explicit. So let me give you the two. So the implicit method is Adams-Moulton. Two-step method. And the work that Adams did with Moulton came up with implicit schemes. Okay, and this can be actually rather difficult if F is not very easily separated to where you can find out the values for yi plus 1. So this one is y naught, again, is equal to alpha, and y1 is equal to alpha 1. So yi plus 1 is equal to yi plus h over 12. This one is 5 times f of ti plus 1, yi plus 1, plus 8 f of ti yi plus, I'm sorry, minus f of ti minus 1, yi minus 1. And this one, where I, again, is did I mess up on the last one? Yeah, I certainly did. I forgot 1 here. I is equal to 1, 2, all the way up to n minus 1. With the local error, minus 1 over 24, y to the 4th derivative of y times h to the 4th. Oh, and this is evaluated at some CI. H to the 4th. And again, this is for ti minus 1 less than or equal to ci less than or equal to ti plus 1. Okay, so that's 2 of them. All right, there's actually a 3-step explicit, a 3-step implicit, a 4-step explicit, 4-step implicit, etc. The one, so let me give you I'm going to skip the 3-step because I can give you all of these, but they're in the book. All right, so Adams-Bashforth. There's no apostrophe on Adams. Four-step. Well, let me see here. I have the 4-step, the 4-step. Adams Bashforth. Three-step. And Adams Moulton. This is implicit. Okay. Adams Bashforth. Fourth step. Okay, remember all the Adams Bashforths are explicit. Okay, so the fourth step for Adams Bashforth is you have to know y naught is equal to alpha, y1 is alpha 1, y2 is alpha 2.
Excuse me,
Yes.
ma.
Yes.
The one you're writing, is this for the fourth step?
Yeah, I am. Yeah, because I'm going to take a picture and send you the details for this. The other
Okay.
ones, I didn't want to skip them and then you think that they don't exist.
Okay.
They do exist. I just am not going to do a whole lot with them.
Okay.
Okay. I didn't want to do a whole lot with them right now. And so but I didn't want to skip them and then you think that they don't exist. So that's why I'm writing them, but I'm not going into detail with them right now.
Okay.
Okay. So I'll just scan this thing and then put it in. But I'm going to say something about the four-step method in a little bit. That's why I wanted to just do a little bit more with this one.
Okay.
Okay. All right. So now you have yi plus 1 is yi plus h over 24 times 55 f of ti yi, and then it's minus 59 f of ti minus 1 yi minus 1 plus 37 f of ti minus 2 yi minus 2 minus 9 f of ti minus 3 yi minus 3. I wish I had the time to show you how they come up with these. It is so cool how they created these methods, where I is equal to 3, 4, all the way up to n minus 1 with local error. And it is 251. Okay, hang on, guys. All right, 251 over 720. Y to the fifth, y, the fifth derivative at CI, H to the 5th. And this is again for, now I have to be in TI minus 3, less than or equal to CI, less than or equal to TI plus 1. Okay. All right, so that is that one. And then of course, there is a corresponding Adams-Moulton. Fourth order, 4-step method. And this is implicit. Okay, so these methods are very, very useful. If you want to try to solve for a particular, you're trying to solve a differential equation. Okay. Let's see here. Then there are what we call predictor corrector methods. And predictor corrector methods combine Adams-Bashforth and Adams-Moulton methods. I want to say a little bit first about these multi-step methods before I get to the predictor corrector methods. Let's see, how much of this do I really want to go through, because we just don't have a whole lot of time. I can't go through, this is the derivation. No, I'm not going to do that. I'm not going to do that either. Okay, so let's talk about briefly the predictor corrector method. So as you can see, the error for these is really, really good. Once you go into higher step methods, then the error gets really nice. I think I had, hold on a minute, guys. Notes. I don't have time to talk about all this good stuff. That's the problem. I'm looking at all this good stuff and trying to decide what of it can I cover in this little amount of time that we have, because we don't have a lot of time and I need to go on. I thought I had already decided what I was going to cover, and then I don't have time to do that either. Okay. So let's talk about the predictor corrector method. Okay, so predictor corrector methods are kind of a combination of the Adams-Moulton and the Adams-Bashforth. So if you remember, the Adams-Bashforth are all explicit methods, and the Adams-Moulton are all implicit methods. So it would be nice if you could predict with the Adams-Bashforth method, and then what we call correct with the Adams-Moulton method. So that means we'll get what we call a guess or a predictor for the next point, and then we'll correct it. So these predictor corrected methods. So predictor combine implicit and explicit methods. And I like these methods. These are really wonderful. This is what I used in my dissertation. They are more accurate and they are generally very stable. So we use the explicit method to predict the solution. And we use the corrector method. I'm sorry, we use the implicit method. Okay. All right. So the method I want to talk about is the Adams-Bashforth Adams-Moulton method.
Let's read this. Let's do this.
Okay, so again, you are given y prime is equal to fy. Then you have that y of a equal to alpha. So I only have 1 point. Now I need to be able to, for the Adams-Bashforth, I know it's a 4-step method. So I need 4 steps. So we could use Euler in order to get those 4 steps, but we know that Euler is not nearly as good as the Runge-Kutta. So we'll use Runge-Kutta to get y1, y2, and y3. So y0 is simply going to be alpha, and we will use Runge-Kutta to get y1, y2, and y3. So now that we have all of those, we will use the 4th order Adams-Bashforth method to get a predictor. So we're going to call that Pi plus 1. Okay, so Pi plus 1 turns out to be yi plus, and this is the straightforward Adams-Bashforth method. So this is h over 24, and then this is going to be 55 times f at ti yi minus 59 f at ti minus 1 yi minus 1 plus 37 f at t I minus 2, yi minus 2, minus 9. And then we're going to get f at ti minus 3, yi minus 3. Okay, so if I was just using Adams-Bashforth, that would be yi plus 1. But instead, we're going to let it be a predictor, and then we're going to put it as yi plus 1 back into the yi plus 1. So now yi plus 1 is going to be yi. So this is the Adams-Moulton part, and Adams-Moulton part becomes plus h over 24. I'm going to have 9 times f at ti plus 1, pi plus 1. So that would have been, that's what would have made it implicit, but instead we predicted that value using the Adams-Bashforth. Plus 19 times f at ti yi minus 5 f at ti minus 1 yi minus 1 plus f at ti minus 2 yi minus 2. Okay. So actually, let me just go back to this where I had multi-step methods. I'm going to go back here for a moment. I may as well write in the Adams-Moulton because we're using it. So I'm going to write it in. So you need y0 equals alpha, y1 equals alpha 1, y2 equals alpha 2, and y3 equals alpha 3. And then we're going to get yi plus 1 is equal to, actually, I'm going to get what I just had on the other one. So I will copy and paste, and then I'll give you a minute to write it down. Okay, so that's what that. So I will give you a minute to write this down. And this is going to be, okay, I'll give you a minute to write that down. And this is where I is equal to 3, 4, ... up to n minus 1 with local error. And this local error is negative 19 over 720, the fifth derivative at CI. And here, CI is between TI minus 2 less than or equal to CI less than or equal to TI plus 1. Okay. So I'll give you a few minutes to finish writing that down. So there are lots of predictor corrector methods. Adams-Bashforth, Adams-Moulton is not the only one. Okay. So in the predictor corrector, it is the same formula, except we were using the predicted value of pi plus 1 in the place of yi plus 1, because we don't know yi plus 1, but we predict it. Now, the derivation of these is really amazing. We use Newton's backward difference formulas and all other kinds of things that we learned at the beginning of the course in order to be able to derive these schemes, but I don't have time to go through all that beautiful stuff. Okay. Or even talk about stability and stuff like that. So I have a few topics that if by chance we run into the fact that we have some time at the end, I can go back and slide some of this stuff in that I had to skip, then we will do that. But right now, that's not going to happen. Okay. Any questions about that? All right, so that wraps up ODEs for us. We've done numerical integration and all of that. So now we are at, there's two other major topics. I know we're definitely going to get to one, which is our linear algebra topic, our linear algebra section. And so I'm going to start that now. Okay.